So I've got a couple of examples here. We want to find the derivative using that limit definition. So before we have found the slope of the x squared curve at a point by using that limit, now we're going to find the slope of that x squared curve at every point. So I want to figure out, if I plug in any x value, what's the slope of that curve going to be? And this is actually going to be maybe a little easier than it seems. So the first thing I'm going to do is I'm going to write out that formula. F prime of x equals the limit as delta x approaches 0. If you feel more comfortable, you can use an h approaches 0 here. Although it would be good to recognize this notation because you'll see it on tests and stuff. And then it's going to be f of x plus delta x minus f of x all over delta x. And so what we're going to do is we're going to use f of x equals x squared here to simplify this right here. So instead of f of x plus delta x, what are we going to have? It's going to be, we're going to get rid of the f. It's going to be x plus delta x squared. So what we're doing is we're putting x plus delta x in for x here. Does that make sense? Okay, minus f of x, which is x squared, all over delta x. And I left something off that's really important here. The limit, yes. So what we're trying to do is see what happens when delta x goes to 0. So we need to be sure that we leave that limit on there. So the limit as delta x approaches 0 of that. And then put an equal sign there. This is just a notation thing, and I'm going to be pretty picky about notation this year. So get used to it. Get better at it if you have to. Don't just write an expression without showing what that expression equals or means. This expression right here is equal to the expression on the line above it, so we put an equal sign at the beginning of the line to show that it's equal to this. If you leave this equal sign off, then this has no tie to this. And I won't know, and I really will know, but I'm going to pretend like I won't know, that you know those are equal to each other. Okay, so be sure that your work has a flow to it that can be followed, and not just followed by somebody who knows what the work should look like, but pretend like a computer's reading it. And if a computer doesn't see an equal sign, then it doesn't think that they're equal. All right. Okay, so what could I do to simplify this expression? Right. Hold on. Let me just say this. Let's try direct substitution right now. Put 0 in for delta x. What do we get here? Yeah, x squared minus x squared, which is 0 over 0. So we get an indeterminate form, right? So we're going to have to manipulate this. What could I do to manipulate this? Yeah, multiply this out. So instead of x plus delta x squared, we're going to multiply that out. So it's going to be the limit as delta x approaches 0 of x squared plus 2x delta x plus delta x squared minus x squared all over delta x. I will say that when we're doing stuff like this, a lot of times h is easier to work with just because the symbols get a little confusing and the x's might get a little confusing. Be sure you keep it straight. Be sure you know what's what. It may help to put the delta x's in parentheses, just as a reminder that these are not x's, but they're changes in x. And what's going to happen with this? So that x squareds are going to cancel each other out. And then once the x squareds cancel each other out, we have a delta x in both terms up here. So what can I do with those? Factor one of them out and reduce it or cancel it with the one in the denominator. Now, the reason we can do that is because we know that delta x is not equal to 0. It's approaching 0, but not equal to 0. All right, so this limit right here is what allows us to cancel the delta x in the numerator with the delta x in the denominator, because the limit tells us that delta x is not equal to 0. It's just going to be really close to it, like really, really close. All right, so this limit turns into something that looks like this. Delta x is still approaching 0. And now after everything is canceled, we have that 2x plus delta x in the numerator. Now, can we use direct substitution at this point? Yeah. We put 0 in for our delta x here, and we get what? 2x. So what does this 2x mean? So the x squared curve is going to look something like that. The derivative is going to be the line y equals 2x, so it's going to be something that looks like that. And so what this tells us is if I pick an x value, say like I pick the x value right here at, depending on the scale, that could be -1. That's probably like -1/2 if it's a square scale. So let's say the x value here at -1/2. I get this point right here on the derivative tells me what? The slope of the graph right there, or the slope of that tangent line. Okay, or this point on the derivative right here tells me the slope of the tangent line at 0, which is going to be a horizontal tangent right here. Or the slope, this point on the derivative right here tells me the slope of the tangent line right there. So by evaluating the derivative as a function, now all of a sudden it's a lot more powerful because we can find the slope at any point rather than at one point. The way we were doing it before, we had to do it at every point that we wanted to know the slope of. Now we can evaluate it as a function and then just plug in points for that function.